Alrighty. Then find and be able to press it. Good. Excellent. So we're very happy today to have Magda Siwek here from the Center for Astrophysics at Harvard, where she's a graduate student for maybe one more year. Yeah. And she's going to tell us about binary supermassive black holes.
Binaries on all scales. Thank you.
On all scales. Yeah. Sorry.
Thank you so much for having me. Yeah, I'm very excited to be here today and to share some results from my new simulations. So I've been a grad student at the CFA for 5 years, working with Lars, and one of the main topics of interest for me has been to look at binaries, such as, is there a laser pointer?
Yes, there is. Sorry, I always forget to tell people about it. There is, this is a laser pointer.
Okay, perfect.
There is also a physical pointer there if you prefer it. But.
Cool. So my main research topic of interest has been to look at these sort of binaries and how they evolve in environments where there's gas present. And so just to sort of name the right terms, this is the binary system here, which is indicated by these black circles. And surrounding it is a circumbinary disk. And you can see from the surface density plot video that I'm showing you here that the circumbinary disk has these sort of stream-like features that leak into the cavity region, which is the dark region here. And these stream-like features are sort of collected by the binary. And this binary system then forms individual disks, often called mini-disks, around the binary components themselves. And so today I want to talk about a variety of these types of systems. And in particular, I want to show a parameter study over mass ratio and eccentricity, and show how binaries with these different mass ratios and eccentricity values evolve differently as they encounter circumbinary disks. And so if this moves forward, yes. And so I like to give away the punchline of the paper. By the way, that was just accepted last week at first. So the punchline of our paper is really about the orbital eccentricity of the binaries in these circumbinary disks. And what we found is that, in line with previous work, the binary does evolve towards a steady state eccentricity. But what is new about our work is that we did this parameter study over mass ratio, and we find that the equilibrium eccentricity that the binary evolves towards is actually a function of mass ratio. So that means if you know the mass ratio of the binary and you know it evolves for a time in the circumbinary disk, we can now predict the equilibrium eccentricity that the binary system ends up with. Wonder if this goes forward. Okay. So first, before I get to this final result, I'll talk about circumbinary disks in a more general sense and how they are important in multi-messenger astrophysics. So I'm going to talk about AGN disks around supermassive black hole binaries, and then there's this scale freeness which comes in when we have hydrodynamic simulations, because we can also apply these results to stellar mass binaries. So both stellar binaries like the ones Gaia sees, but also stellar mass compact objects like the ones LIGO hears. Then I will talk about the semi-major axis evolution that we find in our simulations. And so A, B here is the semi-major axis, and A dot will refer to the semi-major axis rate of change. And so I will in particular show that there are regimes where the binary experiences hardening or inspiral, so this first term here, and there are also regimes in our parameter space where the binary experiences softening or outspiral. And then finally, we'll talk about the eccentricity evolution, and we'll talk about, again, the sign of that rate of change of the orbital eccentricity. And we'll look at regimes where there's orbital eccentricity excitation, but also regimes where there's circularization. And then I'll make some suggestions as to what this might mean for real populations we observe in the universe. Okay, so I like to start this overview off with supermassive black hole binaries. I'm a member of the nanograph collaboration, so something I think about a lot. So in this image here, what are we looking at? We're looking at a galaxy, a set of galaxies that recently interacted with one another, right? And what the observers have done here is they've pointed out these two distinct AGN sources within the newly merged galaxy. And so these are called dual AGN, so there are two AGN within the same galaxy, and they're typically found at kiloparsec scales from one another. And so these are quite ubiquitous in the universe. And then I sort of cheekily put this black arrow in to gloss over all of these different processes that happen within the galaxy to bring these two supermassive black holes together. So there's much to talk about there, happy to talk about it offline. But this arrow here refers to these gigayear timescales that it takes to come from a dual AGN to a binary system. And so once the binary has formed at sort of parsec scales in the center of the galaxy, inflow of gas into the galaxy center will then form an accretion disk around the binary system. And that accretion disk is no longer a single AGN disk, right? It's going to be in a disk around a binary system. And so we don't have observations of this. That's why I put one of my simulations in there to sort of show what we think these binary systems with circumbinary disks around them will look like. Now, another example of circumbinary disk physics occurs when binary stars form. So this is an observation by ALMA where you can see these two sort of protostars forming, and then you can also see that very much like the simulation here, there's a cavity in the center of the disk from which these binary systems form. And there are these stream-like features, again, similar to what we see here, that feed the protostars. So similar to this very different scenario of supermassive black hole binaries, we'd again expect a circumbinary disk to form and potentially impact the orbital evolution of the binary system it hosts.
You said, we see these dual AGN at kiloparsec scales, and we don't see a dual AGN at very small separations. Are you going to speak to that question, or does that remain a mystery?
So I'm not an observer, but I understand is that it's extremely difficult to you kind of resolve these parsecs or subparsec scales in the galaxies where we're looking for dual AGN. So that's one of the issues with observing these systems. There are many other methods to try and infer binarity in AGN sources. I won't speak about the intricacies of that. That's the whole other kind of worms.
I've worked on it a little bit, and we found nothing. We've never found anything that's a convincing small separation binary.
And yet, I think they must be
there's tons of things that must be getting into that phase.
Mm-hmm. So I think it'll be very interesting if pulsar-timing-array collaborations detect the gravitational wave background, because the slope of that background will be very clearly telling us that we have detected a background from supermassive black hole binaries. Now the question of how to detect these systems is another one. I actually have some extra slides. I've been thinking about this detection issue a little bit, and I can show them at the end of the talk. If there are questions, please interrupt me. If I have a lot of time at the end, then let's just keep talking. But I hope there will be a lot of discussion back and forth. Thanks for the question. So another example, and that's just sort of something that's coming up in the literature recently, is the evolution of compact objects on stellar mass scales. And so LIGO has detected a number of black hole mergers, but the way these systems form and evolve remains an active field of research, right? And so one simulation that I'm showing here looks at this common envelope phase that some of these LIGO progenitor sources go through. And it turns out it's actually pretty difficult to eject that common envelope fully. So it turns out that in many simulations, a remnant of the envelope remains, and in the center of that envelope, the binary continues to evolve. And so if that happens, then even the binary seen with LIGO may be affected by circumbinary disk-driven physics. And so what I really want to, the point I really want to make here is that these are three extremely different astrophysical circumstances, right? And yet, all three of them in some way can encounter the type of physics, the dynamics that we're looking at when we study circumbinary disk physics. And so, what is the effect of having a circumbinary disk around a binary, right? Let's be more specific. It remains an accretion disk. So, being an accretion disk, we have to think about accretion rate. And it turns out that the total accretion rate onto the binary system is the same as the accretion rate if the disk had a single object of the same mass at its center. But there is time modulation, and I can speak about this later on. And also, the accretion rates onto the primary and secondary differ. And it turns out, Andrew's group's working this a lot, the accretion rate favors the secondary in the accretion flow. And so the secondary accretes more proportionally than the primary, and that tends to lead to an increase in the mass ratio. The mass ratio I'm calling here Q.
Increase meaning getting closer to what?
Okay.
Yeah, that's what we're gonna say. The percentages, not the absolute.
Right.
Okay.
So I define my mass ratios as going from 0 to 1.
That's the only sensible choice. So good.
Thank you. I
No,
gave this
1
talk.
to infinity works too.
I gave this talk at IAS yesterday, and the sentiment was slightly different. Okay, so we have this mass ratio that grows for all binaries. But recently, in this first paper of this year, we looked at how these mass ratios rates of change depend on the eccentricity of the binary system. And so one interesting thing we found is that that increase in mass ratio is actually non-monotonic. So we've known how the mass ratio increases for circular binaries. Then when we look at slices through the parameter space where we test higher eccentricities, it turns out that the moderately to sort of low to moderate eccentricities, such as 0.2, actually boost the ability of the binary to increase its mass ratio. And that turns over at some point until at the highest eccentricities that we've tested, the mass ratio grows extremely slowly. So that's again another way that these circumbinary disks can reveal themselves in population statistics through changing the mass ratio distributions of different eccentricities at different rates. Another aspect, and that's what I'm mainly concerned with today, is the rate of change of the semi-major axis and the eccentricity. And that's the main focus of the paper that I will talk about today. So I want to zoom in a little bit about on gravitational wave sources and what the circumbinary disk driven orbital evolution means for gravitational wave sources in particular. So I like this sort of flowchart where you think about massive black hole binaries first appearing in the universe as dual AGN, and then eventually they are dominated by these circumbinary disk driven dynamical processes until they reach a gravitational wave dominated regime. And so what I want to point out here is that if you have a large sample of supermassive black hole binaries, and you then apply circumbinary disk-driven accretion onto that sample, you find that the mass ratio of these systems increases, like what I just pointed out. But that is significant when you start thinking about gravitational waves, right? Because if the mass ratio of the system increases, the Chirp mass of the system increases, and therefore the amplitude of gravitational waves that these systems emit increases. And so I like to think about how these kind of binary systems communicate with us. Supermassive black hole binaries communicate with us through pulsar timing arrays, where we see the continuous in-spiral of massive black hole binaries across the universe. And LISA will then probe the actual coalescence of the binary systems. And I want to point out that we did some work where we applied circumbinary disk-driven accretion to these populations. And we found that the populations, such as the Chirp mass distributions, the mass ratio distributions, were significantly affected even by conservative circumbinary disk models. And consequently, the gravitational wave background amplitude increased by almost a factor of 2 by applying the circumbinary disk-driven physics in the last parsec. So it turns out that you can probe the strength of these circumbinary disk effects in gravitational wave background measurements. Obviously, degenerate with many other things. I also want to point out that if the circumbinary disk driven physics is important for binaries detected with LIGO, we can similarly see that the populations are affected by that change in mass ratio. So potentially the mass ratio distributions in some of these binaries are actually carry signatures of gas-driven physics. Similarly, if the eccentricity evolves as a result of circumbinary disk-driven evolution, we might see more eccentric, or we might see residual eccentricities when these binaries merge. And finally, and this is something I won't be touching on too much today, but it seems to me that it's an extremely important question of how spin evolves when you have a circumbinary disk such as this. The inherent nature of this is somewhat asymmetric. The angular momentum absorbed by the two components of the binary may differ, and so you may get different spin distributions and relative spin distributions as a function of these binary parameters. Okay, now I want to zoom in on the results. I want to zoom in on this part of the equation. So we need to understand how circumbinary disks communicate with binaries in order to predict these populations, right? However, these simulations are extremely expensive to run, and so as a result, up until now, most suites of simulations looked at either circular or equal mass ratio binaries. So this regime of eccentric non-equal mass ratio, which is most likely how nature operates, right? It's all, you don't get a perfectly equal mass ratio circular binary at all times. That regime was not fully investigated yet, just because it's numerically extremely expensive. But in order to shed some light on the evolution of binaries as a function of the mass ratio and eccentricity, we ran this really large parameter study. So it's a suite of simulations where we have binaries with different mass ratios. So mass ratios are indicated here, and eccentricities are indicated here. And then we let that binary evolve in its circumbinary disk for a pretty long time, and we want to measure what the interaction between the gas and the binary produces.
Are you running these in the coroutine frame or just plotting?
I was just about to find this out. So every time I show this slide, people ask this question, so it's something I need to say. This is not in the co-rotating frame, otherwise you would, I think in an eccentric binary, you would still see some motion, right? The reason the binary is not moving here is because we are showing snapshots every 10 binary orbits, so it's always shown at apocenter. Yeah. While you cannot see the binary move, and this is really just for computational storage, so I don't want to use terabytes of Lars's storage on the cluster. So we take these snapshots every 10 binary orbits. However, we record all of the gravitational interactions, so the rate of change of the binary angular momentum and the rate of change of its orbital energy at much higher cadence than at every 10 binary orbits.
And is this using some? This is not in GR, or it is in GR. Or is it using some special potential around these black holes?
It's no GR.
No GR. Is it just Newtonian?
Yes.
Okay.
Right. I will say a couple more things about these simulations on the next slide.
And the fact that things look like they're rotating is really just a flickering resonance with this 10 orbit snapshot. This is like a low frame rate video, so it.
Are you talking about the
Yes.
precession of the circumbinary disk?
Yeah.
So that's a real feature.
So that is processing at that rate.
This is processing
I see.
at that rate. So it takes, I think, about
Because
a
something
few
that's
hundred-
processing way faster would alias into that because of the flickering video.
Oh, okay.
I mean,
Just
anyway,
a
it's
slightly different, just at a slightly different
Yeah.
frequency from
Right.
the orbital
Exactly.
frequency would also look like that.
Yeah, that's what I'm.
Maybe a
Yeah,
frequency.
yeah, that's right. So
But I guess that's far enough out. It has to be a much slower process. Yeah. Okay. So I'm
yeah. So
slowly
these,
getting it. Yeah.
So one of the things we actually found in the previous paper was that the precession rate that is well known in circumbinary disks around circular binaries, that precession actually stops when you're in this regime here.
Mhm.
So if you look
Yes.
closely at this regime here, and the lower mass ratio eccentric binaries, there's a regime here where the disk doesn't precess at all.
Mhm.
And this really interesting thing happens where the disk not only doesn't precess, it also doesn't apsidally align with the binary.
Mhm.
It actually aligns, the disk pericenter is offset with an angle to the binary pericenter.
Mhm.
And so we call this disk locking. Steve Lobo has some ideas of what this is. We're not sure yet, but I'm thinking about this also in terms of quantum information. So I really like this topic because it reveals a lot of effects that span many different scales in astrophysics, right? We can think about this with caveats, of course, in the context of supermassive black hole binaries, but we can also look at these features here and ask, can planets form in this?
Mhm.
So there's a lot to do there.
And what, sorry to fix you here, but what's your coordinate system? So, because there's an arbitrary separation of the two objects, but they're not the same separation in all of these cases. Like, how did you set the linear coordinates?
So the scale is the semi-major axis of the binary. That makes sense. But then
But these are at apicenter. Got it.
epicenter,
Great.
so
Good. I'm done.
that's why the
I stand down.
epicenter they're
Got it.
separate. But this is important because it'll actually. I'm glad you're pointing this out because it actually changes some things in the later analysis. So,
Okay. Great.
thank you.
That's beautiful.
Sorry, Magda, can I ask
Yeah.
one more question?
Yeah.
So for the low Q, are the sync particles the same size for both components?
Yeah, I've been thinking about changing the sync prescription to account for sort of proportional sync size between the primary and secondary. But I thought the mass ratio is not that extreme, right? And I did, in the current paper, I ran an analysis where I reduced the sync particle size by a factor of 10, and I found the orbital evolution was not affected by this. So I've been thinking about this. It's just, unfortunately, it's not something in Arepo that I can do while rerunning the simulations from one of these snapshots. I actually just did the math. This took 2 million CPU
Oh
hours.
yeah.
And it's extremely expensive. And I may at one point be able to rerun this, but I think one of the aspects with doing numerical astrophysics that we just have to accept is that you're always smarter after the simulation.
Mhm.
You're always going to learn things, and you're gonna want to improve them. But 2 million CPU hours is a lot.
It's a lot, yeah. It's just that I've actually been wondering about this for a long time, but the secondary at the low Q, the mini disks are fairly resolved. So maybe it's that the torques from the secondary mini disk aren't as important.
Do you mean
No,
in the high?
No, at high Q. Sorry, low Q, 0.1.
Oh, right. I see what you mean. This is also because so when I plot this with Python, I don't think that the
Oh, you don't have
the
okay.
radius of the black
Oh,
circle
I
is
see.
exactly the same as the
So
radius.
it's better. And you have to interpolate from Voronoi onto
Yeah.
All right, that's probably it.
But if I zoom in, you can actually see there's a bit more clearly.
There's more, okay.
However, it's true that when the binary becomes very eccentric, so if you look at this binary system here, the disks at pericenter actually get disrupted. And that is simply due to the rush low.
Mhm.
Yeah.
I mean, if you're going to spend 2 million CPU hours, you better make a good visualization. So this is an achievement here. This is really, really good.
Actually, I'm not on Twitter, but I should be. We won like astronomy plot of the week for this.
Oh, nice.
It's really fun to look at. So thank you.
And it really does show that stabilization of the disk hole.
Yeah.
That's very beautiful.
And what it also shows, and getting back to the context of orbital evolution, is that the gas morphology, if you compare this guy to this guy, the gas morphology reacts quite sensitively to the binary parameters, right? It's just because we have a different gravitational potential when we change these binary parameters. And what that implies then, in turn, is if you have a different gas morphology around the binary, you're going to have a different gravitational reaction of the binary reacting to the background of matter, right? And so the reason I show this plot is it's fun to look at, but it's also very educational. It tells us why we need to run these type of simulations, because we cannot, through theory, predict how this type of gas is going to distribute itself around the binary system. And if we cannot do that, we cannot sensitively predict how the binary is going to evolve as a result of the interaction with the gas. So this type of suite of simulation is really important to predicting that behavior. Okay, so a little fact sheet before we get to the result. So I mentioned already these simulations are scale-free because we neglect some physics, right? If we did full radiation, if we did GR, we wouldn't be able to say this. But I thought for a thesis project where I'm, getting started with something, I wanted to look at the mass ratio and eccentricity as the parameters and how they change the orbital evolution. So this is still scale-free. And you need to set the mass and the semi-major axis of the binary system in order to then obtain sort of physical values for the semi-major axis and eccentricity evolution. So we evolved the binary, we evolved the simulation for 10,000 orbits, but we keep the binary on a fixed orbit. And the reason we do this is because we want to achieve a steady state, right? We want the disk and the binary to be in a viscous steady state. Now it's a finite disk, so it's never going to be in a total steady state. It's always going to be reducing in size as the binary accretes from it. But ultimately, we are looking for that quasi-steady state so that we can then calculate how the binary parameters would evolve where we allow them to. We have pretty good resolution in the cavity, so this is people who speak hydro. This is the resolution, the mass resolution right within that center of the cavity, and that is because we want to resolve the single disks or mini disks to a good degree, and we want to be able to show how the stream-like features rotate around the binary. We want to be able to resolve this pretty well. And so, amongst other things, we record the accretion rates. We also do record some kind of spin evolution, although this is highly dependent on the sync model. And I have some ideas about what one could do with this, but it's not part of this analysis. And then more importantly, we use the gravitational and anisotropic accretion torques to calculate our binary evolution model. And so gravitational torques, I think, are self-explanatory. Anisotropic accretion becomes important because some of these binaries lose their disks at some point. So if you think about a free sink orbiting in a background of gas, there's going to be anisotropic accretion of gas. You can think of it like a headwind. That is going to transmit momentum into that sink. That's going to change the orbital evolution of the system. And that actually becomes somewhat important for larger sink radii, and also becomes more important when the eccentricities are sufficiently high. There's a conversion study in the paper you can look at, but that's all I will say about that.
These are 3D.
These are 2D.
These are 2D.
These are 2D.
And it's a thin disk, presumably.
And yeah, the thing you don't say here is how you set up the disk.
Yeah.
Do you put it into some like alpha disk or something?
Yeah, I should say that. So this is a locally isothermal disk. It's got an aspect ratio of 0.1, which really just changes the viscosity mostly. What was the last question? Sorry.
I was just asking what was the setup of the disk?
Yeah.
And the disk, does the disk extend way outside the simulation, outside the box here?
So the disk extends to 50 times the semi-major axis of the binary. It's fairly low mass, and that just scales up with the accretion rate ultimately. So the accretion rate actually parameterizes the orbital evolution rates, and so as a result, this is almost irrelevant for what we're doing.
Is it self-gravitating, the disk?
No, it's not.
Okay.
So this is one thing that I've been thinking about. If we were to allow for self-gravity, we could potentially say something about star formation and AGN disks, because obviously there's a lot going on, right? Like if we have an AGN disk around the binary system, that disk is going to experience much more shocks, right? And other important effects that might lead to, for instance, star formation. could be an interesting.
So what is the box size?
The total box size is 300 times the semi-major axis of the binary. I just really do this so that I can allow for viscous spreading of the disk, and the disk can be freely.
But if it is 2D, why is it expensive?
Excuse me?
If it's 2D, why is it expensive?
That 10 to the minus 6 there, I think.
Yeah.
It's the resolution in the cavity that really drives this. Yeah, the resolution right here in the cavity is really what drives this. And this is, you might think, oh, this is a tiny aspect of these simulations, but no, you want to actually resolve these circumsingle disks quite closely because they actually dominate the orbital evolution of the semi-major axis. And I will get to that.
And also you need to run thousands of orbits.
Yeah, and I choose to run, maybe it's 10,000 is slightly overkill, but I like to be able to show that we get the viscous spreading rate that's predicted by theory, and we do. So.
And this is an alpha disk or constant?
This is an alpha disk.
Of 0.1.
0.1 alpha disk, right? So not constant mu. But I compare to some of the models that use constant mu, and it doesn't seem to make a huge difference, which is encouraging, although other aspects of the viscosity will make a huge difference. So I visited IAS yesterday and had a lot of conversations about how MRI is the way to go. Yeah.
So I want to ask, do you have a
Yeah.
video, by the way, showing from the initial conditions to where you stopped here?
I don't. Do you think that the initial conditions could teach us something?
I mean, everybody tries to forward model anything from the initial conditions. So
Yeah.
because I wanted to see like how this changed over like the evolution of the system from the beginning. But
Yeah, I mean, that would be a pretty long, well, I guess I could think about this. I think the reason that I'm not showing this is because at this point I'm quite convinced that the initial conditions are erased because we run for so many viscous timescales that the disk is pretty much viscously relaxed out to 20-30 times the binary semi-major axis. I've rerun these a couple of times, and I've also done tests where I leave the cavity initially full, so I don't start out with an initial excision in the circumbinary disk, and it doesn't make a difference. It just takes longer to get to the steady state. So it's really just an exercise in agility.
And once you set all these parameters, just because it's a low mass disk and it's scale free, there really is just an accretion rate now. Once you set these external parameters of Q naught and E, everything just scales up and down linearly with this accretion rate / density in the disk, right? It's
Right.
all the same.
So yeah,
There's
exactly.
kind of no, so this is solving a kind of very well posed problem. This is very nice because a lot of things are very dirty, like with all the different, you've extracted out a very clean problem that is scale free and has one free parameter basically.
Yeah.
Once you
the
set
hope.
E and Q.
Yeah, that was the hope. It was just understanding dynamics based on very simple parameters. That's why we initially didn't go with the idea of having the disk allowing for self-gravity in the disk. Because if you think about that, then you're never going to reach a steady state, right?
No.
So it's just one of those problems that when you start them off from scratch, you have to go through all of the literature, understand what's important, how you can set up a problem to compare with what others have done. And that's what we've hopefully done. So I don't know what we're looking like for time.
It's 2:36.
Oh, okay, we have plenty of time then. So I want to show the semi-major axis evolution next, and I want to go over these regimes of in-spiral and out-spiral. And so the first thing I like to do, so I can sleep at night, is compare my results to what has been done in the literature, right? So that's, to me, that's an important first step, understanding if the 0th order result can actually compare to what we know or what's the consensus. And so the 0th order question is, how does a circular binary with varying mass ratio evolve in a circumbinary disk? And so in this plot, I don't tend to show too many complicated plots in my talks. I just want to show a mass ratio dependence on these orbital evolution parameters. So this is the semi-major axis, which is parameterized by the accretion rate. I could equally parameterize this by the surface density. And what this plot here shows us is at which mass ratio for a circular binary does the binary experience hardening or softening. And so we found this result, which is consistent with what has been done in the field, that at low mass ratios, the binary tends to inspiral or harden, whereas at high mass ratios, it sort of breaks through that zero axis and wants to actually soften, expand. And so here are a few citations of people who have done very similar work, been very helpful in setting up this problem in my thesis work. So so these are consistent.
And is there a simple explanation for that? Because my brain is like, don't they always inspiral?
Yeah, it's the reason I think why your brain says that they inspiral is because the outer circumbinary disk will tell you that it does. There's been resonance, there are resonances in that disk that analysis that I'm not too familiar with predicts that the circumbinary disk causes the binary to harden or inspiral. But it's really important to resolve that cavity region to some degree in order to capture this behavior of outspiral.
I see. So it has to do with the detailed dynamics inside the cavity.
Yeah.
So Chris Tiede did a really nice analysis of this last year. And he also showed that this is a perversity of Mach 10, right?
Yes.
So
Yeah.
for truly thin disks, it's inspiral.
Yeah, I'll mention that for sure. Yeah. There are many caveats with this. I think that, I'm going to show you all of my results, but I don't think that this is a closed case. Right?
Mach 10 means
0.1.
axis ratio.
H over
0.1.
0.1, which is kind of a slim disk.
Yeah.
Slim disk,
Yeah. So this is
not a thin disk.
extremely dependent on the viscosity in the disk, but that makes sense, right? Because if this result is dependent on the dynamics of the gas in the disk, then it's going to depend on the viscous torque of the disk inward and the gravitational torque outward, and the viscosity of the disk is going to tell us how much gas can actually penetrate the cavity and therefore provide this behavior of outspiral. But it's extremely hard, for me at least, to quantify or put my finger on what exactly is causing the outspiral. We know sort of where it's coming from, and I've been having some ideas of tests one can do, but it's not, I don't think it's a one-line answer.
What are the units of the y-axis?
Disagree.
Well, again, to what Chris did, he took
Yeah.
time averaged
Yeah,
and in the shape of the kind of cavity wall, that
Yeah.
material causes the outspiral.
yeah,
And as a function of Mach number, the amount of mass that piles up in that kind of cavity changes.
so I think it makes sense to think about, well, if the gas tends to be ahead of the binary, it's going to accelerate the binary. If it's behind the binary, it's going to decelerate. But I still wonder why. Why is the gas ahead or behind of the binary? That's the question. I don't know if I have a good answer to it.
Right, yeah, Y is complicated, it's
Yeah.
it's hard to not here.
Yeah.
So,
It's
but-
complicated.
Yeah, no,
Great.
That's why I have to do simulation, if you can understand
It's
it.
true. One can do these
Yeah.
these time averaged density profiles and see
And then it
where's
should-
the
Right,
gas.
whether it's leading or trailing.
Yeah.
Right.
Right. But I would like to understand why that is. And recently I read a paper that looked into the shape of the binary potential and found that there are these so-called saddle points in the potential that allow gas to leak into the cavity at certain points. And I wonder if one can do something with that. If there's a sort of analytical explanation for, at least we know where the streams penetrate into the cavity, then we can maybe say something about where they do that and how often. Maybe there's something there, but I think there's a way to go.
What, the y-axis, what are these units? Are these like per orbit? Per
So this is so the semi-major axis rate of change. So this is not per orbit. This is essentially, this is unit free because it's parameterized by the accretion rate, right?
well, it's a dot, which is like, I would assume that was per time.
Yeah,
Over
but then
A.
it's divided by m dot over m.
which also has units of per time.
Yeah.
Right, oh, it's divided by.
Yeah.
Oh, that's not a.
Yeah. there's
Okay,
a-
so I should think of it as I say, so if I'm
Yeah.
growing 1%
Yes.
per billion years, then A dot over A is 1% over.
That's exactly right.
Okay,
Yeah.
okay,
And so the way I calculate this value is by integrating over the last 7,000 orbits of the simulation. So I take 3,000 orbits for the disk to relax, and then the last 7,000 orbits I average over that. And I've checked changing that window slightly back and forth, and it hasn't made a difference in the result.
yeah, so the summing major axis changes percentage-wise about the same rate as the growth itself. Okay.
So now if we take another slice through our parameter space and we look at an eccentricity of 0.2, the result kind of overturns itself. So now we see that at low mass ratios, these slightly eccentric binaries tend to soften, whereas at higher mass ratios, they tend to harden. And this becomes, this sort of continues as we go to higher eccentricities, here 0.4. But what I'd like to point out here is that the amplitude of the semi-major axis rate of change is actually much higher now. So that in spiral and out spiral is is quicker and more efficient. Of course, something annoying happens. At 0.6, we get this weird non-monotonic behavior, right? Where first we get this out spiral solution, then there's hardening, and then the binary softens again. But at the highest eccentricities we've tested, it was clearly all moving inward. And so this is confusing, right? So these are very non-monotonic regimes that we're testing. Clearly, the morphology of the cavity causes different behavior based on these different mass ratios and eccentricities. But I always like to think about, take a step back. Why did we do this? Well, we did this because we wanted to understand how the orbital evolution changes as we look at a larger parameter space, because that's a more physical thing to do, because the universe doesn't work in, zero eccentricity, mass ratio 1, only binaries. And if you think about the numbers of simulations that lie underneath that zero axis, you can kind of see that at least when the binary is eccentric, in spiral tends to be a more common solution. And now obviously that's going to depend on what binary parameters are most common, but if everything is equal, in spiral it's fairly common if the binary tends to be eccentric.
Do you have the feeling that if you densified your eccentricity grid, imagine you had 20 million hours or 200 million hours and you did eccentricity of 0.01, do you think this would all change continuously, or do you think there really is some kind of very sharp features in this?
So I did some eccentricities between 0 and 0.1. I didn't show them here. There wasn't sort of a wild fluctuation.
So you feel like it does kind of just continuously deform from one?
It's not extremely sharp everywhere. That would be scary, right?
Yeah, right.
It's continuous somewhat, but there are some regimes where you see this very non-monotonic behavior, and you can see this especially.
Yeah. And Paul Duffel scanned the space by smoothly changing eccentricity and found there was one sharp feature. I think it's the same one you have, right?
Yeah, that's the same one we have. I had a plot where I compare my work directly to what Paul and Dan have done. Probably should have done this here, put this in here for this audience, but it's in the paper,
Yeah.
so definitely this is all very consistent with what Dan and Paul have done. Yeah.
I guess the way your code works, do you have a bunch of these binary systems that didn't run at the same time so that you can sample all of these mass ratios, or could your code run in such a way where you just fix the mass ratio and then run from many eccentricities?
I just fixed the mass ratio.
Okay.
So the mass ratio, even though the binary is accreting, it doesn't actually evolve. The mass ratio stays the same throughout the 10,000 orbits.
Okay, so you could, in principle, do this for many much finer set of eccentricities to keeping the mass ratio the same.
Yeah, I could. Again, so I've done a few more runs between 0 and 0.1, but I didn't think the behavior was sort of extremely significant. Maybe I should look at where exactly this goes from positive to negative, but it seems pretty smooth. I think there's a plot in the paper where I show this, and I'm happy to show you later. So more simulations would be great. More simulations would also be great because there are features in the accretion variability that we're going to try to pick up with some machine learning models. Everyone has to at some point, right? You want to have a lot of simulations so that the model can train on a lot of simulations and detect different characteristics. Right now, I've not dipped my toes into machine learning quite yet, but yeah, more simulations would be great eventually. So again, if you look at this table, which is showing eccentricity on this axis and mass ratio on this axis here, each cell gives you the rate of change of the semi-major axis. And I color-coded this so that red signals softening or out spiral, and blue signals in spiral or hardening. And one of the reasons I like to show this is because I've been speaking to a number of people who like to do population synthesis codes, and not only for black holes, but also there are people who are interested in star formation, right? Stellar binaries. And in these models, as far as I'm aware, circumbinary disk-driven evolution has rarely been discussed. And a table such as this is extremely cheap to incorporate into a population synthesis model. So if anyone's interested in working with this data, let me know. It was 2 million CPU hours. We need to make the most of it.
Yeah, but again, it's all Mach 10.
It's all Mach 10, definitely. But I wonder how Mach 10. So true for AGN disks, that's a problem. But
for stars, you're right. That might be
could
right. Yeah, it might be appropriate for stars.
Yeah. However, the alpha there is much lower than what we do. Yeah.
So it's a big parameter space.
There's a multi-dimensional parameter space.
So the AGN disks are supposed to be much thinner?
Much thinner, yeah.
Okay.
Yeah.
Even at that, like.
Okay.
I mean, are there certain values that these are the values of Mach, these are the Mach values that will be most important for real objects? Is it basically those two, like 10 and I guess whatever the value is for AGN? Is that what you want it is? Okay.
Probably, yeah.
Okay.
I mean, because that is just one. I mean, you are saying there's a lot of parameters, but actually you have a pretty well posed problem, so it seems possible. I mean, wall clock time, this was a month or 2 months?
2-3 months restarted.
Yeah, of course there's restarts, yeah, but honestly, yeah. I know how it is, but in principle, once you have a working piece of code, you could build out a block of results.
Yeah.
With including the alpha parameter or whatever the Mach number.
So the problem is if you then also vary alpha or the h/r, you also have to run for longer because it takes more viscous time scale. As long as you reach the viscous time scale. So that's a bit of a problem.
I see, yeah. Fine, yeah.
So I like to show another table here. If you don't like this non-monotonic behavior here, this table here shows what the orbital evolution of the semi-major axis would be if we only include cells or a gas that's outside of the cavity region. And so when we do that, if you focus on only this column, that column becomes all dark blue, right? And that is, again, because the circumbinary disk, rather than the cavity, causes this inspiraling solution.
Sorry, what's blue and red? Forget that.
Sorry?
That was just what's blue and
Blue
red?
is in
Inspiral.
spiral.
Okay, got
Blue
it.
is negative in spiral, red is.
Okay. Yeah.
And so there are some caveats here. So we've cut out the same amount of the cavity for each simulation, but obviously the cavity responds to the binary parameters. And so this may be why we're still seeing some outspiral here, because the cavity and also the binary orbit is larger than that 1 semi-major axis radius that we're cutting out. Again, in hindsight, you are smarter, but I also wanted to be consistent because we're already varying so many things. don't necessarily want to cut out different amounts of gas from each simulation. But again, running this again, I would maybe vary the cutout radius from the cavity using some analytical models that studied the eccentricity and mass ratio dependence in the cavity size. And so I want to mention definitely there's a well-established dependence on viscosity, this paper. 3D effects are neglected, radiation, MHD, there's a lot to do. I do really want to move on to the eccentricity evolution because this is one of the results that actually.
You asked for questions.
Yeah,
You came to the wrong place.
The eccentricity evolution is one of those results that may actually be insensitive or much less sensitive to all of these caveats that we just discussed. So, so I will show again a very similar plot, but this time I'm going to show you the mass ratio on the horizontal axis and the eccentricity rate of change on the vertical axis rather than the centimeter axis rate of change. And again, just to visually distinguish the two regimes, but the circularization and the eccentricity growth. And so you obviously have to do a sanity check first. If we have a circular binary, which is shown here with these blue stars, the eccentricity rate of change is 0, just a symmetry argument, right? But then if we start up our simulation with a binary with a non-zero initial eccentricity, we find that throughout the regime of mass ratio tested here, the eccentricity grows. And the rate of the eccentricity growth increases with mass ratio as well. Now, if we then keep taking slices through our parameter space, so here we've got an eccentricity of 0.4, we see that this trend of increased eccentricity growth with mass ratio continues, but we start seeing features where there's circularization. And then if I finish off with a couple of high eccentricity runs here, 0.6 and 0.8, we see that all of these simulations here want to circularize the binaries. And so what that implies is that there is some kind of cutoff value in the eccentricity, right? It also implies when you look at, for instance here, a mass ratio of 0.4, you imagine your binary on that type of mass ratio on an eccentric orbit of 0.2. Your eccentricity is going to grow until it hits around 0.4, and then you're going to start to circularize. So that's a sort of steady state solution, right? It's an equilibrium eccentricity value. And you can see this even more clearly when you look at this table of the eccentricity rate of change as a function of mass ratio and eccentricity with all of the simulations now, just to keep the graph not too messy. Now, to remind you, red is positive, so we have eccentricity growth in these red cells here, and blue is negative, so we have circularization in those values. And you can kind of make out there's an attractor here, right? There's a diagonal here where red switches to blue. Yeah?
Does that mean that moderate eccentricity should be rare because everything should either circularize or become extremely eccentric?
We'll see. Depends on the mass ratio. Yeah. I'll show the regimes in a second. Yeah. But it essentially means that for each mass ratio here, we have an attractor, right? For each mass ratio, we have a transition between eccentricity growth and circularization. And then if we interpolate between those models and we find a more exact or a more precise value of the equilibrium eccentricity at which that sign change occurs, we find this really beautiful plot where mass ratio is here shown in the horizontal axis and the equilibrium eccentricity towards which the system wants to evolve on the vertical axis. And so this is almost a linear function, right? We can see almost the binary eccentricity that the binary wants to evolve towards, that equilibrium value, is almost a linear function of mass ratio until it sort of saturates at a value of around 0.5. And so yes, you might get low eccentricity binaries at low mass ratio. We expect this to continue downward because in the regime where the mass ratio gets extremely small, we know from Goldreich and Tremaine that will cause a circular orbit. So we expect this behavior to continue downward for smaller mass ratios. So why is this happening, right? We can answer this question, at least for me, the answer is not very satisfying for the semi-major axis study that we did. But we can have a slightly better answer for the eccentricity rate of change. And to come to this answer, we can again do this test where we look at how does the equilibrium eccentricity change when we only include, and this is the green line here, when we only include cells or gas that's outside of the cavity region. And it turns out when we only include gas outside of the cavity and in the circumbinary disk, there's similar behavior, right? We have the same, we have almost the same steady state eccentricity in the high mass ratio regime. There are some slight bumps here, which could also be the same bumps that we still see in the semi-major axis rate of change, which is still positive at these low mass ratios. But we ultimately see similar behavior. The mass ratio and equilibrium eccentricity grow together and saturate at an eccentricity of around 0.5. And so it turns out that there was work done about 30 years ago. There was a really nice paper by Steve Lubo and others that looked into the balance between co-rotation and eccentric Lindblad resonances. And they did some very, the SPH simulations at the time, a few hundred particles. They evolved these circumbinary disks for a few hundred orbits, and they looked at the shape of the circumbinary disk after a few hundred orbits, and then did some analytical analysis of the resonances occurring in these circumbinary disks. And even though they weren't evolving the cavity very much, they weren't doing any sync particles, they were just looking at the shape of the circumbinary disks, they were able to come up with equilibrium eccentricities based on this resonance interaction between the binary and the disk. And they found that based on resonances, the equilibrium eccentricity should be around 0.1 for low mass ratio systems and should be around 0.5 for high mass ratio systems. And so again, this is using extremely different numerical techniques and very low resolution in the circumbinary disks. And yet they found very similar results to the ones that we find today with our really high resolution simulations. And ultimately, their analysis suggests that this equilibrium eccentricity is a purely dynamical effect that is caused by a balance between eccentric Lindblad resonances, which tend to boost eccentricity, and co-rotation resonances, which tend to decrease the eccentricity and circularize the binary orbit. And so I know right now there is a student at Clemson also working on expanding this kind of analysis to different viscosities, and we'll see if viscosity treatment changes this result. But my hunch is that if a SPH simulation from 30 years ago finds similar result, maybe we'll find, maybe we're converged at this point.
Actually, that would be bad because this is truly an observable, like this is really an observable, yes. Because, and so you'd actually like it to depend on the fundamental properties of the disk, because then we actually would have an observational handle on the disks in which these systems were formed.
So we're observing that because if we have two disks and if we find a binary and we measure,
it suggests that if you can measure the binary mass ratio and eccentricity, you could tell whether or not you're on this trend.
You could tell if circumbinary disks have its own domination.
If this was set by a circumbinary disk, and if so, what was the physics of that disk?
Yeah.
It feels very much like, I mean, of course, it's hard to find a system that's so clean that you could make a native observation of this, but it's.
But maybe if you do many of them,
you might see a peak in the distribution of Q, and like in the QE plot, when we measure a lot of binaries, maybe you would see a ridge that represents this.
are there like X-ray binaries so you could determine these things for? Is that a thing?
I feel like an X-ray binaries to gas morphology is very different, right?
I don't know.
I'm thinking stellar binaries, like
Post AGB.
yeah, or even better, like eclipsing binaries.
So I've been
Post AGB.
trying to find a time to look at some Gaia data to do this. I think it'll take also a bit of statistical analysis to figure out which kind of systems we expect these effects to dominate in. But I think stellar binaries, just because of the numbers, are a great way to start looking into this.
I mean, but you need a stellar binary with like some massive enough thing around it.
Yeah, that's why post-AGB is interesting.
Post-AGB, but also even just the formation of stellar binaries, if they formed in the same
Yes.
disk.
Protostars,
Yeah, like protostars, exactly.
Oh, I see.
Yeah.
But also-
Yeah, you don't need a black hole in the center.
No,
It's
it doesn't have to have a black
No,
hole.
Okay.
You don't need a black hole.
No. Another aspect that I forgot to mention is that this kind of trend also doesn't at all depend on the sync particle treatment, which sometimes can be a bit iffy in these simulations. But because everything is sort of dominated by the circumbinary disk rather than the behavior right around the binary system or right around the sync particles, it's essentially agnostic to the sync particle treatment. So another point I want to make is that you only need the binary to accrete around 10% of its initial mass, which again probes that surface density in the circumbinary disk, or it's just a feature of parameterizing the eccentricity evolution by the mass accretion rate. So you only need to accrete the binary. You only need the binary to accrete 10% of its mass in order to reach that steady state eccentricity. And another way to look at this is just with a semi-analytic toy model that I did at the end of finishing this project. So here I started off 3 different binary systems with these 3 different mass ratios at an eccentricity of 0.1. And then I interpolated the table of the eccentricity rate of change, and I wanted to know if this thing is accreting at Eddington rates, how quickly is it going to get to its steady state eccentricity. And the steady state eccentricity for each system is shown here with this dashed line. And so it appears that the steady state eccentricity is actually attained within just a few megayears, right? That's just another way of saying the stop data time, like 10% of that. But I still think it's instructive to look at this. Just a few megayears and you're well within the equilibrium eccentricity. And so that's significant, right? Because if we think about AGN disk lifetimes, that's totally consistent with what we tend to think AGN disks lifetimes are. This is also important if we think about then later on probing the population statistics of different types of binaries using, for instance, LSST, pulsar timing arrays, and in the distant future, LISA. So I want to point out one more aspect of, because we talked about the semi-major axis evolution for quite some time. If we know the final eccentricity that the binary ends up at, we can also then highlight the semi-major axis evolution at that final eccentricity value. Now, obviously, we have to interpolate this table, but I like to just show roughly what we would expect, right? So for low mass ratio binaries, which are these 2 things here, we see that at or near the equilibrium eccentricity, the binary tends to expand. But then at the higher mass ratios, when we look at our semi-major axis evolution, we see that that is negative and the binary would actually spiral. And what's really fun about this, right? You compare it to this previously known result, it's exactly the opposite, right? So you never know.
But those low Qs are increasing, right?
Right. Did I say?
No, just the point is that
Oh,
they're
right.
unsteady, yeah.
Yeah.
So they might go out for a while, then come back in.
Yeah. So the low mass ratios will increase in mass ratio, but the timescales of that I think are a factor of 10 longer than the timescale of the evolution of the eccentricity. So I think of it like an HR diagram of it, you know. We're going to be moving along Q. So you're going to, yeah. So it's going to be maybe a fun animation to make at some point, interpolating all these models and showing the tracks of the binaries, the function of these orbital evolution prescriptions. So if I think didn't the schedule say it goes till 3:15? Or is that wrong?
You can do it. Go for it.
Okay. So I will
That's
show.
because sometimes there are questions.
I want to show some very preliminary results that are really related to the work I do with the nanograph collaboration. So one question I was asking myself is, can we probe the circumbinary disk-driven orbital evolution with, say, LSST, when LSST gives us a bunch of massive black hole binary candidates? and we plot their properties, do we see anything in the distributions that hints at the contribution of the circumbinary disk driven effects that we just discussed? And so one thing that we do in the collaboration is we look at cosmological simulations, and from those we get information about the massive black hole binaries that should form in the universe. Now then we get those massive black hole binaries. They're obviously not resolved in these cosmological simulations, but we semi-analytically evolve them forward until merger. And so that gives us, as a function of redshift, a lot of different binaries and their evolutionary stages. Now, we then give these binaries some state eccentricity, that's just a thermal function, and we allow that eccentricity to evolve through, for instance, stellar scattering and gravitational wave hardening. What we find is that at 5 milliparsec scales, and I chose 5 milliparsec scales because that might give us a few cycles in LSST within human lifetimes, we see that the eccentricity distribution of the binaries in that population synthesis model looks something like that, peaking at around 0.1, the mean around 0.14. Now, if we then include circumbinary disk-driven effects, and I only included circumbinary disk-driven effects that amounted to an accretion of at most 10% Eddington, only at binary separations where circumbinary disks may form, we find that there is a huge sort of tail here, right, that just cuts off at around an eccentricity of 0.5. And so that is a clear signature of the gas-driven eccentricity growth that we included in our models. And this nice sort of bimodal distribution is indicative of these different effects at play. We even found that when we then let gravitational waves take over eventually, even though the gravitational waves circularize the orbit, there's still residual eccentricity left. And Jonathan Drake's paper has also done this analysis and found that there are residual eccentricities left behind due to the circumbinary disk.
When you say there's a residual eccentricity left, you mean at the time the merger occurs?
Yes. Yeah. So based on that, Lisa may see eccentric mergers, not, eccentricities of 0.8, but
LIGO right now just has upper limits on eccentricities, or does LIGO detect any eccentricities right now? It only gets a couple of orbits, so I doubt it can see an eccentricity. Can it? I don't know I don't remember.
I don't think they're well constrained.
I don't remember them
I don't think
saying.
they're very
But Lisa.
Lisa,
can do
yeah.
Yeah, Lisa
thousands
will
of
kill
orbits,
it.
that'll
Yeah,
kill it.
Lisa will
So
kill
even
it.
tiny eccentricities.
Yeah,
yeah. Lisa will be much more sensitive to this. And I'm definitely interested in that, and also interested in seeing what LSST might yield for us in this context. So I have taken up too much of your time, so I will leave out my conclusions, and I'm around all day, so please come speak with me. Thanks.
Are there more questions? Sorry, I didn't mean to express it that way. Are there more questions?
If I keep coming back to this point that you've structured this well-posed question. Now let's get a little more serious. Are there really just 2 more free parameters? I mean, if you stay within this disk model where there's an alpha and a Mach number, are those the only 2 remaining free parameters?
I mean, there's the inclination of the disk, right?
Yeah, right.
So actually, these simulations are set. So one of the reasons it took 3 years to set these up from scratch is because I designed the mesh to allow for free rotation of the disk.
Oh, really?
So Lars 5 years ago told me, why don't you do inclined disks around binaries? And I did. I did set the problem up with this in mind. It just turned out the eccentricity and mass ratio got more interesting at that point. But this code does have capability to simulate that extra parameter of inclination. Now, alpha, Mach number, I mean, what else is there? It can allow for magnetic fields. I had a very interesting conversation with Jim Stone yesterday, and we talked about how would the magnetic field morphology look like if you keep spinning up and allowing magnetic field lines to arch over from the circumbinary disk edge to the circumsingle disks. These are all questions you can ask, right?
Yes, right. Right, but yeah. No, and there's a lot of ways to make this problem way more complicated. But I'm liking the fact that there's this very close to a well-posed question
Oh,
here,
thank you.
and I think, and as you said, it leads to a lot of phenomenology, like your kind of HR diagram concept.
Yeah.
And obviously, a lot of that might change as you make things more complicated, but it's clearly relevant to understand this case first,
Yeah,
or
I
in
wonder,
parallel, maybe not first, but in parallel with that.
Andrew, are there more parameters?
Yeah, I was gonna say, it's a really messy one, we probably shouldn't admit it, but you asked, so the sync prescription.
Yeah.
How, that's
Yes.
not the event horizon of a black hole.
Right, of course not, yeah.
So
We
gas
don't know
that disappears from there, where did its
Yes.
angular momentum go?
Yeah, right.
So that's a tricky one, it can completely change.
Yeah.
Are these
Actually,
torque free
These are,
sinks?
no, but actually, so I did add an analysis in the paper where I decreased the sync radius by another factor of 10,
Right.
and it didn't have an effect.
Yeah, not just the radius though, but
Mm,
just whether you swallow the angular momentum from the
yeah.
sync material, or whether you put it back into the
I thought
gas.
from Alex's paper, it seemed to me that there wasn't a huge effect from doing this, or is there something you don't?
Well, it's
I
an
mean,
effect.
You must be able to calculate the rate of angular momentum
Yeah,
disappearance, right?
right, there's
Right.
also
Whether
a
that-
spin, you could also do spin dots under certain assumptions. We assume that everything really is getting eaten. Then you have a S dot for each of your.
So I think the absolute spin rate of change is very murky, but what I think it might be more well posed is the relative growth of spin. So if you make the same mistake twice, you might
Good, yes,
You
good,
might-
love that.
no, you might actually capture something about just the angular momentum that falls in towards each black hole just because of the orbital track, right? So that there might be something there, but there are many caveats, and that's
But
why.
those are observables too. In
Yeah.
the stellar case, the spins are observable.
Yeah, I don't know if in the stellar case, if you wouldn't run into issues because we're not simulating winds.
Well, of course, yeah, I mean,
There's
yes.
a lot of,
Yes.
but his attitude is right. For this well-posed simple problem, I think Mach number, alpha, and then the sync prescription. That's basically it.
Because that feels, I mean, if you don't care about your carbon footprint, that does seem like a possible study there.
Yeah. It is.
Yeah.
Yeah. Well, there's a huge,
We're not gonna open up that conversation fully, otherwise we all have a lot to answer for.
I'm starting
We
to
really
respect
do.
the garden of the CFA. I feel like I'm trying to work against my terrible carbon footprint.
Don't worry, many of us spend more of it on flying
Yeah.
than you do in your data center.
Let's thank Magda again.
Okay, I'll log out of this Zoom. But I'm in the visitors office,
somebody
so
planning
come speak to
dinner?
me.
Okay.
anyone can sign up for dinner.
Oh, there's dinner?
Yes. Oh, did you know?
We're
planning on
we've been terrible about communicating anything to Magda.
If you are free,
It's
we
not
would
been
love
a
to.
well-run visit,
Yeah.
I feel like.
I'm around.
Okay.
Okay.
Tim mentioned something to me, but I wasn't sure if there was a reservation or anything.
Yeah. We usually go around. We'll probably at 6.
Okay, great.
Okay, good. Thank you.
Thank you.
Yeah,
Thanks for having me.
There's a slightly better.
And there's a
where we
faculty meeting in a
actually
few minutes.
Yeah,
so,
unfortunately.
against the.
So I'm gonna
But I think we should only
Okay.
do that. I think
And
we
we're
should
meeting at 4:30?
work at.
Yeah,
this level
I'm
of
also in this
approximation
meeting.
we can
I might be a little bit late,
And then ask
depending on how
ourselves,
late it
do
goes,
we
but
want to
I should be out by
make
4:30.
Okay.
Actually, it gives me an excuse. I'll
Because
just.
I
Very
always like
nice.
to
Can we
do
do
the
more
easiest thing for.
Yeah.
us, whether we-
Actually, I have a few minutes now.
Go.
Oh,
Easiest
sure, but
we
I
can
don't want
even
to make
take
you late.
action.
No, I have 15 minutes or 14 minutes.
Okay, great. Yep.
And you remember Marcus,
Figure out
right, from
exactly
Santa
what the
Barbara?
effect
Yeah.
is, but
Yeah.
it's
Hey.
where every flavor is.
Are you coming to dinner?
We even have generative models for Blazor spectra.
All right, let's get
So
coffee.
we could do that in a good way.
And can I confirm that I understand why we need to use the AV times not Vega? It's because by definition AV has is normalized as like a flat.
It's because it is normalized to an F nu equals 0, S nu equals 0 spectrum. S nu equals 0 spectrum.
The one, oh, the one he's talking to her now? Okay. Okay.
here, if you put in counter curves, seven and go from there's not going to be any other presentation today. I don't think so. Okay. So let's say you have like this. So if we look at the definition of the, let's say these are curvaces. So is like the plus 2 interacting on this thing. Should give me that's the idea. Just to show that this formula is the same as yours. So for one question, so we have delta m, and I guess we will get the correct result if we assume that the d2 plus 2 times d2 plus is just m plus. So isn't this part 0? d2 plus 2 times d2 c minus c minus. What I'm saying is this contribution. Oh, wait.
Well, no.
Because if m plus is this guy,
Well, it is that plus L0 and L1.
or m.
Wait.
Oh yes. So then is, I guess that's exactly the point here. This is delta m, basically for L larger.
One thing that I know that the C plus is really something you don't like, and I agree, I don't like it either.
No, I'm just trying to like find a physical meaning for that.
I know it's not a well-defined thing, but the transformation that we do from Schwarzschild metric to Bondi coordinates does not depend on the way you wrote the Schwarzschild metric at the beginning. So we tried to do it in harmonic, isotropic, and I think another one, and we always end up with a C containing this L equal to 0 and L equal to 1 harmonics.
Yes. So okay, so the question is, how do you read this C from the metric? How do you read it?
Yeah, so
Can you maybe explain a bit?
yes, so essentially okay. So let's say we start one black hole, because what we did was one, and then because in our case the asymptotic, we assume that the asymptotic method will be a superposition,
Okay.
which is fairly good assumption, I hope. And okay, let's suppose you have some metric in some coordinate. Okay, that's your starting point. What we did was essentially redo the same thing that Veneziano-Vicovisky did, but to one order higher. So we say this is going to be, let's say that these are the harmonic coordinates or isotropic, and these are the Bondi one. And so this one is for the new the new metric Bondi 1 will be this Bondi harmonics harmonics G harmonics. We know this, we know what these are, and then we say, okay, suppose that this X differ from the harmonic one perturbatively. So they are X plus some delta. And we found this delta order per order in G, essentially by, of course, imposing like GU is 0 and etc. You know, that's essentially what we did. The same thing that Vanessa and Vikovitzky did, but one order higher in G, because in that way we could read off the angular momentum aspect. That was the main point. And like, okay, say you have that. The U of Bondi is going to be the U of harmonic, where U of harmonic is just T minus R, plus some order G correction, plus some order G square correction, 1, and the same for the other components. But let's focus on U just to be consistent. To find this expression explicitly, you will have some differential equation to solve.
Yes.
When you solve this differential equation, you have, of course, you have the particular solution, so the solution plus a residual function that essentially is the BMS freedom, change of it's going to be a BMS transformation. And if you don't, if you set this to 0, say you do the naive thing and say that the solution to the differential equation is what you find and the complementary function is going to 0, then you find this C appearing in the. So
can we go over that part?
Yes. Yeah, the problem is that the order G cube, I don't have any written notes and everything on Mathematica.
No, I mean just like the generic form of the equations. I just want to see when it exactly appears.
Okay, maybe I'll try to be.
So basically my ambiguity, I mean the point I still do not understand is that I understand that the C appears in the combination of CAP, and I'm just curious, when you make this transition to reading C, I assume you're reading it from CAB or somewhere else.
No, it actually appears in N.
N? N A in aspect?
Yeah.
Where? Because in A, I mean, where?
So in A, so we started from a metric of one body, in which essentially the one body follow this trajectory. So in the metric it will be, in the metric will appear V and the momentum of the body.
Okay.
So we transform this into Bondi coordinate, and in the Bondi coordinate, of course, we will have still V and P.
Okay.
And what we found is that M is the usual one. But NA, the NA is minus U DAM, as usual, is essentially the same, where B is just N cross B, and C is coming explicitly from the solution to the differential equation.
Okay, no, that's exactly. So this C that's appearing here,
Yeah.
one step before this, where was this C? Because either you have to define it somewhere, I mean in the metric or somewhere, because this is not a field that's very natural. That's
No, indeed, it comes. I mean, in principle, you could have said, okay, let's find the transformation. Since you have the freedom to add a complementary function, let's set this to 0. But if you don't set the C, if you set the complementary function to 0 in general, the solution to the differential equation spits out this C. Essentially,
Oh, so you
it spits out this combination together. That's what it's saying. Then we recognize that there is a piece that depends on B and a piece that depends on P. But essentially, it's telling you that NA is some complicated function that can be rewritten in this way.
I understood it correctly. So this C that you're defining here, is it the integration of constant of integration?
Of the differential equation?
Yeah.
No.
It's not, okay.
It's just that you do the transformation and delta U you find in, I don't know, like a differential equation in R going to be G something. You solve the differential equation, you say delta U going to be G your solution. Actually not an R, going to be something like that.
Okay.
Plus some complementary function.
Okay.
We set this to 0 and we just take this.
And then where is C?
It's just that then you write the 0, 0 component of this. No, not actually not the 0, 0, the 0 A component of this. You expand it up to G cube with all the differential equation, and you find that N A it's like an expression depending on P or the moment of the particle and B, and it can be rewritten in this way where this depends only on the moment of the particle. That's where it comes from. Just by matching the metric with the expression of bonding.
So let's see. Now you can understand it perfectly. So there was no C, there was some expression.
Let's say NA is equal to some expression. Yes, exactly. NA is some expression of the momentum and the B, the impact parameter, and it can be written in this way.
So and then you from the expression for the A which you read from the metric, you separate it to two parts. One is depends on B, one is depends on P, and then the one that depends on P, you name it C.
Yes.
Okay. So
indeed, it's nothing. If you want, we could have said that it's just NA is the object that we found. But it was natural to isolate the part that depends on B, because if we go back to the one single object and you compute Jmu, that is this thing, and if you take this N and take the definition of comparatal, so essentially just take this N and take B, then J will give you
correctly. Okay, maybe that's like the main source of confusion. Like probably the name of C, although for the L larger than 2 it is the same C that's appearing in the shear tensor, but for L equals 0 and 1 it's like a bit tricky to call that part
I
of
agree.
C.
I agree. And indeed, what we the explanation that we could give for the L 0 and 1 is the one that Veneziano and Wilkowski gives. That is, when you change coordinate, you shift the origin, and L equal to 0 and L equal to 1 in this C are telling you that you are measuring the angular momentum no longer in the same origin of the harmonic.
I'm so confused by this because I mean
it's not okay. We should probably not call it C.
Yeah,
I agree.
So let me show you actually the like he has like this expression for the NA, the same boosted frame, and then everywhere here C is larger than 1.
Yes.
And then at one point that he is like doing thing. I mean for the L equals 0 and L equals 1 is like precisely name them x0 bar and xi, which are like the position of the central
I
line.
see. Okay.
So yeah, so because now this is a physical thing. This is not something you can fix by hand, or this is not some ambiguity. This is like the physical.
Yes.
So okay, now I guess the story is different. So
yes. So the problem is that it's now okay. So and so it works as long as you know the solution for the metric for the full space, and by in a sense extending your validity of the bonding metric up to the origin, which is what you can't, but you know, if you work particularly in G, you can say you can define origin in bonding. And that's what Veneziano Mikulski was telling you essentially, that when you go from harmonic, which is where the QFT people are doing computation, to the bonding, you have an extra translation that we wanted to separate from the B, because we want B to be this, we want J to be given by just B cross B. That was so we should probably, and indeed in the new version of the paper that we are going to put online, we probably call this actually P plus C, where C contains only greater than 2, and this is a like translation transition.
Yeah. Because I was so confused with that.
No, I know.
CAB that is minus 2A.
Absolutely.
Yeah.
Now, you know, the problem is that both me and Kim are not, and Filippo, we are not expert on this subject. So
Okay, so now I think the story is different, because we are trying to add a term that only involves the center of mass
yes.
to the flux. So it shouldn't be that hard. I mean,
And the last thing that I want to mention is that since this translation from the origin depends on the momentum, is different at sky minus and at sky plus.
Yeah.
So the difference between the two is something that you can measure. So okay, rather than call it C, call it P.
yeah, exactly. I was about to write this, that because in this form this is different, because you are telling people, okay, this is exactly the position of the center of mass.
Yes.
And
Okay.
this is the density of the momentum of the
Yes.
center of mass.
Yes.
And
yes.
this is always the term that you can add like to our term, because for us that flux is, as you saw, like this is in a way blind to the contribution of the flux from
Okay.
the center of mass.
Okay.
So that part is like, if you like, is like
Yes.
for the system itself. But if you are moving the system around,
Mhm.
our formula does not have that, and then we have to add the term that exactly corrects for that.
So you're saying that what we added in a sense should be the 0I component, and so the flux of the position of the center of mass.
Yeah, I mean, I can write that in there. This is the position of center of mass, and this is the density of the momentum of the center of mass. So this should be that part. And then again, this is like exactly the part that our formula does not have, that because that starts from L larger than 2. So
Okay.
we always have like this freedom, and it makes sense that only in the center of mass it agrees, because in the center of mass
The flux
it is not moving.
Yes.
So, but if it's moving and you do not have that part, okay, you have to add it. Okay, now I think, okay, it just remains like to work out the explicit form of, I mean, explicit in terms of the like some neat and clear expression that
Yes.
reflects that, okay, this is just a center of mass term
Yes.
we're adding.
I'm just still a bit confused.
Which one?
Let me think, because so what? Let me think a bit. So what we are saying now, yeah, so that really doesn't really, I don't really need this anymore. But so what I think I did then is that yes, so the invariant is still given by the integral over the rectangle, then you have NA minus the piece when PC like this.
The YA.
Yes, sorry, y.
Okay, yeah, this is for the rotation.
Yes, and then you will add the extra y, p, a, y, a if you want to boost.
Yes.
Okay, I'm fine with that. And indeed, okay. So what we would write in the paper is probably be this. Which is the same, just integration by part, right? And this C only contain L greater than 2.
Yes.
And this is the definition on which everyone is agreed. But then we would say that Q of t, which is the one, let's call it Q of t, which is the one that Vivekja and Bini computed, is J in BMS plus this translation P.
Okay, this is more than translation, right? Because it has two pieces. One
Yeah.
part from the center of mass, and there is this other part that we also have like a flux part for L larger than 2, right? That term that's proportional to the curly C and then delta.
Yes,
Because
but
this is
shouldn't be this one.
no. Exactly, this was the one thing. This C, I mean, is a graviton field, right?
Yes.
But this curly C is not a graviton field. It's like a shift of the graviton field. It's like you are choosing a reference frame.
No, okay, yes. Yes, of
So,
course.
yeah,
Oh, no,
so-
I agree.
yeah,
Okay,
so
I
you
understand
want
what
to
you
write
said.
it, to subtract
Yes,
the
okay, I
curly C.
understand.
Yeah.
Okay, I agree. Okay, yeah, we would probably, we need to think about this, but this curly C in our case would pop out as delta C, where again this is only L greater than 2, and it will coincide with the curly C that you have found, which is the one of Veneziano, etc. Just because it pop out because we are asking the final state to be again the superposition of black holes. So okay, let's say this is delta JBMS, which is given by this one, so delta QFT plus the translation bit. So this should be this one, right?
Yeah. The translation, you mean like the zero?
The zero I component,
yes,
of what we call C.
Yeah.
Okay, yeah, no, with this I'm fine. I'm just wondering if it's something that it's going to be valid to all order in G. So if at higher order there not going to be something funny where radiation is okay, which is probably required in more further study of higher order in G. And I'm still confused though on how a boost will transform this object. Say you had this at minus infinity in the center of mass, and you want to compute it in the rest frame of one particle. How this will change?
Okay, so there's first one common, like I think you know, but there is more like to mention it again. So this JBMS, people call the JBMS without this guy.
Yes, okay.
So for us, like if you add it, we have to change the name to not be confused with the original BMS.
Okay.
That's one thing. So the second thing is your confusion with the calculation, how you do that, or with the result.
Yeah, let's say it's really let's call it BMS.
Because the way you do it, you start from the Poisson bracket, and then is just is some tensor, depends on the A, B, C, D, and then there is a D of the delta U minus U prime. This is at U and Z bar, and this is at the U prime, Z prime, and the Z bar prime.
Okay.
And there is a delta.
Yeah.
Okay, you start from this and then you build everything, right? So from this you go up to the flux. Right, the flux, I mean, for example, the DOM is, if I remember correctly, is 1/4 into n minus 1/8 n squared. And then the m is just integral of this guy. So commutator of the super translation, which is just the Tm and some field, is just you go through that. Okay, right everything. Okay, and then for the Lorentz generator, we have different distribution, and all of them are more or less the same. Basically, the difference is on the boundary terms.
Okay.
So, but up to boundary term, everyone agrees that this is a generator
Okay.
of the Lorentz.
Okay.
Okay, and then you write that in terms of the flux, YA, UNA, so and then with the du. Now you are integrating on the whole square plus.
Okay.
And then, okay, we have like this big expression for the, in terms of the CAB and the NAB. Okay. And then basically to compute anything with the, so you want like to know how a boost changes some of that operators, you compute QY and that operator here with top of the commutator. Okay, of course, I think like few pages like
No,
to compute this, but I mean you will get what you want. I mean that I think that's the like most principal way of like computing these objects. And okay, what we did like to get rid of the ambiguity is what to start with the CAB, which does not have like this boundary graviton, but it is actually delta C, which is, or like it is C hat, which is C at U minus C at A minus C.
Okay. Yes, the dynamical C.
Yeah. And then you pay first, you find all the commutators involving the C hat and the N, and later you add the soft degrees of freedom with the introduction of the dressing. And what the dressing does is simple, because let's say you have the QY. Okay, the main point of this construction is that by definition it basically commutes with the soft degrees of freedom. So anything that you have built here would commute. So if you are looking at the soft charge, the Q soft, or the C itself, and by this, of course, we mean L larger than 2.
Yes.
Yeah, just avoid clutter, we just do not mention that anymore. So this is 0.
Okay.
Okay, and then why would we dress that? This looks good. The reason is that the Q soft is not as good of an object. So Q soft is basically du of the and okay, this is an object, but you want it like to be a more elegant object, and that's what dressing does. So once you dress the Q soft, it basically replaces this object with the N. So it would be du of the UM. So okay, it also is a function of some function N.
Yeah.
So if you like, this is just okay. So okay, and for boost, we are looking at this commutator for which the d dot phi is not 0. That's a boost.
Okay. Yeah.
Yeah. And then you calculate that.
Okay, and yeah, because my question was under boost, you essentially, as Massimo said before, you instead of having a y, you will have y times the boost matrix or whatever. And then my question was how, okay, and minus, I know how it transforms, and minus it's painful, but you can find how it transforms. But C minus, you said it doesn't acquire an L 0 and 1. If
Oh, okay.
that's
so-
the confusion that I still have. The definition of Orbital, let's say, evaluated at minus infinity.
Yeah, this doesn't have first two modes. The first two modes are coming from this guy.
Perfect. But does he transform nicely under boost, saying that under the boost it remains without the 0 and 1 harmonics here?
Yeah, I guess that's, I mean, because once you have constructed that object, you can look at the transformation rule for that. Okay, so the thing is that under that QY BMS,
Where BMS is the, let's say, the compare
yeah,
definition.
yeah, this, now this is like your new expression
Is
for
the
the
new
charge.
Okay, yes, yes.
So you compute that on C, and what you discover is that it leaves the invariant, and on the right hand side you have a 0 or a equal 1.
But if you fix it to 0, they are not there.
Yeah. At least what it means that you cannot make them with this Lorentz transformation.
But you are saying that now the Lorentz transformation are generated by this charge, not the old one.
Yeah, I mean,
Okay.
most of them still are a representation of the Lorentz rule, in the sense that both of them satisfy this equation.
Okay, no, okay. So you're saying that also this QY BMS will satisfy Lorentz algebra, and so it's a valid representation of the. Okay, no, it's that where I was confused, because I was applying this to that.
Yeah.
And you're saying you're not allowed, or you're not doing a good thing if you're doing that.
It's not consistent, but this is basically the conclusion of the last week.
But it's also what Wang and Yao are doing, right? If I understand correctly.
I'm not sure actually.
Well, because if I understood correctly, they, I mean, I should reread the paper. It's quite hard, but they are saying, okay, my invariant charge Q tilde is this Q plus this extra piece. This Q is invariant under Lorentz, but this Q is invariant under Lorentz using that charge, the old one, right? So if you don't have this, this thing is invariant under Y and I.
Under the old QY?
Yeah.
I mean, it's not. It will just give you like the upper thing, because without this term, it is just an old charge. So this is like the QY, and then its commutator with the old QX is just a Q of the Y and X. The mixing is that if you compute QY with the QBMS X and see what you get. But if most of the Q's are BMS or are all the old version of the Q's,
It will give you Lorentz algebra.
yeah, the Lorentz algebra will be fine.
Yeah, because the problem is that their proof that the charges were invariant under Lorentz was telling you how each field transforms, and then putting it inside the formula and see that the charges was invariant. But that transformation of the fields, it was related to the old boost or the new one. That's what was not. I think it was related to the old one.
Maybe. I mean, as a clue, I mean, you do that, right?
Because I have it. I mean, I was reading with a lot of time because I'm no mathematician, so it's hard.
What I remember I read their first paper, and then they were the way I understood the explanation was that they had the expression for the charge, which was not invariant by itself, but once you look at the flux or you subtract it at 2 times, the difference is invariant.
Probably yes. Probably you're right. But what I was confusing is that they're defining a boost just as a relation between the two bond system. So I was convinced that this definition of boost is this one.
Maybe, yeah, because it doesn't look it's specifying.
I think it's that one, and then they are giving you.
Yeah, okay, yeah, it should be the boost, because
it should be the traditional boost.
No, I think it should be true for either of them because
Okay.
this is just a Lorentz transformation, right? If you have a boost in the null line coordinate, it acts like a dilation.
Yes.
And it should be true, I mean, it should be true for any representation of the Lorentz that we are building.
True. You're right. This is just a particular. Yes. This is how it will act on the coordinate, but the representation.
Okay, but where that it might go wrong is that how these quantities.
Exactly. That's what I was confused.
No, okay, let's see.
Because if C transforms like that, then C acquires some equal to one and
Yeah, that one is a bit. Okay. It doesn't seem that it is like separating a larger matrix.
but at least okay, the extra piece, fine. But at least the flux, the hard flux, when you consider like the charges consistently and the transformation of Lorentz according to the new charge that you define is invariant and equal to 2 don't get fixed.
Yes.
That's what you prove in the previous paper, right? Okay, then I'm fine with that. Because what I was afraid and what we were afraid now is that since you have this extra translation, you know how to define, and then there is a boost that made C acquire some L equal to 0 and L equal to 1 harmonics. It was natural to include this L equal to 1 and L equal to 0 into C because the boost transforms that C. But if you're saying you just need to be consistent on how you have the charges, how you define the charges and how you define the representation, then I'm fine with that. Okay.
Yeah, so this is like saying that, okay, what we have found is not a BMS in the traditional way. We have found a Poincare.
Yes. Okay.
Plus something that commutes with this thing.
Yeah.
So an infinite extension which commutes with this Poincare.
Okay. Yeah. Okay. In a sense, yeah, isolated the super translation.
Yeah. So you can just look at any problem by separating like the higher modes from the these low modes with 0 and 1, and then you treat these two as just a regular variable general Lorentz representation. But for L larger than 1, they just commute. So they will not get transformed. Yeah, and that's basically how you solve the ambiguity in the.
Okay. No, now it's definitely more clear.
Yeah, but still, yeah, there is like this is a bit. I mean, the also covers is that even the fact that you are separating you have like do this non-local thing that you have to separate from the rest is not very satisfactory, but
It works.
yeah, it works. It's the price you pay for that.
Okay. No. Now it's definitely more clear. So the angular momentum and the flux charges transform nicely under Lorentz. They don't acquire any L0 weird thing. And the L0 and L1 that we need to add to this flux in order to be consistent in our frame is the flux of the center of mass, which under boost of course changes because you are changing the. Okay, no, now it's definitely more clear.
Yeah.
It's.
I think you could just write that in terms
There's
of
still the question of how to fix it in general, because with the way we fix this center of mass, it's actually find the solution. But this supposes, this means that you need to know the solution at minus infinity of the metric, and it's not something that you want in general. I mean, how do you fix this extra piece in general? That's.
I guess you are. The fact that you needed like the information from both infinities is because you are looking at the flux.
Yeah.
And that is by definition, okay, you are subtracting 2 times
Yes.
u2 u1.
Yes.
So what you can define each of these quantities at a given time. You do not need like to refer to the earlier or the later time. And for this you just add this is just my intuition that you just add the center of mass contribution to the angular moment. at that moment.
I see.
So, and this is something that is local in time. Of course, if you look at the flux and then you subtract the two, you will have something non-local in the sense that you will have like the integration from U1 to U2. But for one moment, it is a well-defined object. And it should not be like, and okay, it should be also covariant, right?
Yes.
Because we have like this form of the charge that has one piece which is covariant by itself, but is not enough. Is
Yeah.
We miss this 0 and 1. But this one also should have a covariant form.
Okay.
And once you have that, then the question is what else you can actually add to that thing.
Okay.
How many possibilities do you have? And if in a word, this thing does not coincide with the result of the paper, I don't know what to do.
Yeah. But yeah, the problem is that I think I rerun the mathematical file with the expression of time. But if you compute this should be your expression for J in the rest frame of particle 2. This is just beta, probably expanded. Yeah, it's probably expanded. And these are just because I fixed, it's probably a mess written like that. Just that I'm more familiar with Lorentz indices than BMS still, so I always convert them in Lorentz indices in the computation. But essentially, it's this one.
Oh.
And instead of YADA, we showed it.
Yeah.
That you can write in Lorentz indices just because it's more familiar for people coming from my background. You can write it in this way. And so what I have in the mathematical notebook here are just this and derivative that I have already applied. So that is your expression, and when evaluated in the rest frame, you get these, where P is the momentum at minus infinity of the particle moving, but you should have not got these two, because that's not what Finendam were figuring out. That's where we started from.
Yeah, okay, yeah, let's actually add this piece and see if that kills the two.
Yes, okay, let me see. But what would it be, the texture piece?
Yeah, I'm thinking of the hot
I think if we look at what we wrote, it would be. I actually think I did this computation.
enabling should be that expression, the same expression that we have. So it should be T, and then we need the first mode of C, and we need a YN. and then it should act on the C, and then with the M, but now everything being restricted to the first mode. We'll not call it C, we'll call this X of the center of mass.
And you should have delta M, you see, or M.
It should be M, right?
M,
Because okay, so this.
But then necessarily you get the correct result, because that's essentially what we wrote in the paper, right? Because that's essentially.
Let's see if, yeah.
Okay. Forget delta C. Imagine that this is delta T. That's essentially what you're writing, right?
Yeah, this is okay at a given moment, and this is the X would be basically the okay, probably should be here. Because then YADAM is like the position of the center of mass.
I see.
Then this is C. Sorry. Is YADAM, which is also equal to md dot y. This corresponds to some momentum, right? Because the translation is made with this operator mt. Translated this guy. So if I want to naively guess the form of the angular momentum, I have to cross this thing with the this is momentum with the basically X. So this C, which contain L equals 0, sorry, L equals 0 and 1 also, encode the position of the center of mass, and the M for L equals 0 and 1 encodes the momentum of the center of mass.
Okay, yeah.
And then, but I'm not sure how I fix like this number in front.
Yes.
I guess, yeah, for that we have like to exactly write everything with the correct coefficient and just do it properly. But the form of the extra term would be this. But yeah, instead of C, like, do not confuse it, and Massimo will get angry if we name it C.
No, I now I understand why all the confusion of our
Yeah, we have like to
notation.
write it as X, and the X being the position of the center of mass.
No, but now I understand why you were not understanding me. I'm sorry.
Yeah.
I was making okay. So
Yeah,
because
we are referring to two
C
different
is just okay. C is just L greater than 2 always.
Yeah.
Okay, I now understand. Okay.
Okay, the first two modes doesn't matter because they do not appear anywhere. But
Yeah, we fixed it because we want that's the explanation that also Veneziano-Mikovitsky gives. That is they give it in a very cryptic way. That is the light cones emerging from the center of mass.
Yeah.
Whatever that means. But anyway, the physical thing that I learned from that is okay. There is when you do the computation in harmonic and then you go to bonding, there is a translation because you're changing origin essentially.
yes.
And so there is a change in the position of the center of mass in the bonding coordinate with respect to the harmonic one.
Yeah.
And that's what we were missing then. Okay. And that's what yes. Tamur still was not convinced, my dear.
I mean, I expect someone if he sees like a covariant formula to be convinced. I mean, what else do you want?
No, Tamur is not convinced about a problem in angular momentum. That's the problem. That's okay. So we had, but it was a very interesting discussion. But yeah, he said the bond angular momentum should be fine, and we were like, cannot be, you know. But okay. But the problem is that in post-Newtonian on bound orbits, the bond angular momentum is perfect. Just because then we suspect, and I think that also.
Okay, but what do you do if we make a super translation?
Yeah, no, the problem is that they don't have any superposition, any way to see a superposition in the formalism that they have, and I think that Ashtekar actually showed that in a bound system, the memory contribution to the angular momentum is actually negligible, and that is why the angular momentum computed with Bondi fits very well with numerical simulation and everything. Just because for bound system the memory is negligible.
Yeah, but okay, like Massimo has like his famous example that you can add a soft radiation to your system. Let's say you have like this a binary object that are,
Yeah.
and then you add a soft radiation that's like passing from very
Mhm,
far away with a very large.
I agree.
How do you have to add that contribution to the angular momentum?
I totally agree. But that's not what the system that's not what post-Newtonian theory would study.
Yeah.
Post-Newtonian theory would study this without any background or any radiation.
Yeah. Okay. So you are basically
You are
making
ignoring.
restricting like the boundary condition.
Yes.
And that restricting boundary condition, I mean, you can also do that like in the case of gravity, and you can kill the BMS and like just
I agree.
yeah, that you can also do. But the point is that people do not do that. Why? Because if you if you basically relax the boundary condition, you will have the new charges, and these new charges are not infinite nor zero. So, and this is, I guess, how physics works. If you can have, if your system has a non-zero charge, you just add it to your physical theory.
Yeah, no, I agree.
Yeah, we do not, right? We do not know away like the finite charges, so like the things that usually help us solve the theory. And in this case, yeah, the only reason that people allow for these BMS charges is that they are finite charges and they're conserved.
Yeah.
So if you are throwing them away, you have like a reason why would you do that?
No, I agree. That the point is that when the post-Newtonian computation started, historically was really just the goal was really just compute higher order, and also angular momentum was not really an important observable. What they were trying to compute was the gravitational wave emission and the energy carried away and the waveform. So the angular momentum, it was not completely, I think it was not really understood. And also, the computation started in the 80s, something by the Moore and others, which was really pioneering in this sense. And they were not aware of all this. But that's also where the confusion is coming for us, and I think for you, because these are two communities that are making and not necessarily speak the same languages. But it's important because I think that at least I hope I brought a bit of my community into your discussion and underline the problem in this. And
it's actually very interesting that I brought two different formalism. The one like post-Newtonian, and then you are doing something that I think is like very different from this kind of calculation. You are getting the same result.
Yes, indeed. And our main objective was to correct the mistake that we had in the very first paper that I published during my PhD, that were computed angular momentum using the Bondi flux, and say, it's the same result of the Moore, we are all happy with that, and then no, because we computed in a frame that was not the center of mass.
Yeah.
And then people will start arguing, but you can use Bondi for a frame only in the center of mass, which doesn't make sense, because when you define the Bondi frame, you're not defining, when you define the Bondi angular momentum, you're not defining any frame. Yeah. And so we were super confused about this, and that's why we had useless. But it took us a while to get acquainted with the Bondi formalism, to be honest, and I'm still not super familiar with everything, with all the aspects. But that's but I'm really happy that I managed to be here and talk to you, because it clears a lot of confusion in general. No, it's true. It's in also because most of the paper on BMS are very mathematics.
Yeah.
And
it's actually okay. If you look at our previous paper, I think it will be unreadable because of like the if you look at the chart, the two-line chart.
Yeah.
And then the subtraction from the plus infinity minus infinity. But yeah, I mean, after a year, I can say that we could have written that like a bit simpler, and like skip some of those things. But yeah, usually when you tell like this business, there are like this biggest expression that basically this is just I don't know what's the name for that. This is like the legwork or something. You have to just like write everything in terms of commutator and do integration by part, make sure that you're keeping everything.
Yeah, the other thing that I not that I don't like, but it's a pity of all of this is that if you want to do practical computation, you can't use this.
Yeah, yeah,
And that's a pity though.
yeah.
Because we would like to compute the G, because now the angular momentum is known up to G cube, the mission. And we say, oh, okay, let's compute it to the cube. Yeah, find the n in Bondi up to G cube. It's nasty, really nasty. So no.
Yeah. I have no idea how you actually write an expression for NAV. I guess
I
it
have
should
no
come
idea
in.
I mean, up to G, it's okay, it's nothing at all. It's very easy. But then the waveform, actually, the waveform, it has been computed, and we also computed it. But in momentum space, there's no analytic function that can express the waveform. I mean, I basically couldn't find it, and also Veneziano couldn't find it, and also Lamour couldn't find it. So the best that you can do for NAB or CAB, let's say, at order G or GQ, G squared, it depends on how you scale G, but anyway, at next leading order, you can write it at most as a integral over some one-dimensional parameter of some Bessel function, which is awful because then you have to square it to compute the flux, and it's impossible. In direct space, you can find a close expression in terms of time, whatever that means. But anyway, in terms of some time variable, but then derive it and square it is a mess, and then you cannot integrate over time. That's what we found. So we actually have a CAB next leading order, but if you try to differentiate it, then the flux is NAB, and contract the two, you get a mess that is impossible to integrate. So no, it's impractical. And indeed, I think we'll try to compute the G cube, but using this loop technique that I was showing in the presentation, but that means essentially not computing the flux, but the left-hand side. So we know X, we know P, we know how to rewrite them in a loop Gaussian way, and then we solve that. Essentially, not the flux. But that's also, that's.
So can you actually, from that order G, read the behavior of the n near omega equals 0?
I don't know.
I'm not sure. It's always an interesting object, right? Because then that would give you the soft charge, right?
Might be.
I mean, that's because soft charge actually the n du from plus to minus n plus. This is by definition n tilde 0.
Yes.
So the behavior or the zeros component of the Fourier transform of this n is always an interesting object. That it should basically coincide with the, I think, the K2.
Well, I'm not sure, but if you want, the expression of the waveform is written in this paper. It's written in plus and cross polarization, but and it's a mass of notation. But what F is, so F is essentially NAB because it's a transplanted part of H, if you want. And okay, they scale it like that, and it's asymptotic because it's the one where R is. And they say there is from here a zero order computer, so contribution G, which is the static part, and then the next leading order. And the next leading order is where all these, yes, I will define up here. They are all function of this tau, which is the proper time. But
Over is there an expression in the moment?
in momentum space, you cannot find an expression. That's the problem. And I spent 3 months of my PhD trying to find an expression in momentum space, and we gave up because it was impossible. And in momentum space, you can write it as integral of some Feynman parameter 0 to 1 of Bessel function, Bessel 1 modified K Bessel function of the argument was a square root of some complicated function that depends on n, the direction of the emission, and the momenta of the two-point body, because we will focus on two body. So yeah, integrate that.
You will get the
Yeah, but yeah, it would be nice if we had an n, but we don't have it. So yes, I think I will be here. Yes, tomorrow and Thursday, Friday, maybe in the morning. But yeah, and then next week I will have
Okay, I will try to like write the expression tonight or tomorrow and then
yes, but it would be nice to if we in the end have this extra piece which actually is really there in the flux of the center of mass. Then I would be very happy with that.
yeah,
And finally, I can put this business behind because
are you changing subject?
no, but
Oh, you mean this paper? This
at least this paper. I cannot deal with this paper anymore. It's too much. Thank you.
Okay, thank you for the discussion. See you around.
Yeah, everyone. Do you think reimbursements for the Astro? No, we didn't pay. Oh, okay. Cool. Yeah, by the way, it was great. It was a packed place. Oh, good. I'm glad to hear.
Maybe we could have a seminar, but because of these components, the speed will be under free, but that concept conflicts with your meeting, if the meeting takes place.
So we can like skip 1 week or even like if everybody agree we can like have it sooner or later. So
Okay, so but it would be okay to accept.
yeah, of course. Thanks for asking.
It's working.
Maybe I can share some. I tried it. Like I tried
I don't know. I just visually
You don't want to go to the park with me and Clayton and me.
No. But you can't do it. Feel and also you can. Oh, you have to you have to add the extra. So if they don't file it, they you have to file it yourself and totally get.
All the years, you know, but I mean, but they just said they got a letter from IRS saying that they owe $60. I'm gonna do it. I don't wanna be on the right side. $60 is fine.
$6 for that, for what?
I don't know, because I mean, they say, no, you owe $60. I don't know. I don't know. I mean, they just charge you fucking money. I mean, they have power over you.
But you file your.
I told you many times we have a friend from the village. Avery has to pay more than what he has to pay. Like, he has to pay 1,000. He gets a call saying you owe $600.
But maybe that's yeah.
Well, I mean, it's just the stamp and the envelope and all the shit and information and my social security
I
number.
don't
And my,
trust that.
I am not going to call IRS and say I'm gonna pay.
No.
I'm
Go
gonna pay
to
$60.
NY, go to NY tax department and show them the envelope.
Well, the thing is, Andy also got it. I got it.
Phone calls are scams. I don't think it's
Yeah, and also it's an IRS envelope. It's also $60. Okay, but true. I mean, I am already happy that that even if I have to pay $60, I'm still not making money. But yeah, I mean, they can make a little money as well. You have to pay $60. I mean, no, I don't like spending $60, but even like it's that this. Like last year was 23,000, which was like.
Yeah.
There you go. Imagine when you're doing all the shit, like when you're only rich,
And
they
you have
ask
to
you.
pay 3,000 and federal. It's like $400.
Yeah, that's how it
Thank
goes.
you. I don't want that.
Yeah. The thing you do all the information, please put some vendors like little rocks. I mean, like it's your result is that. You click on the PDF and they tell you you owe $3,000. And you just like you grab the corner and that's you can't do anything now. You owe them $1,000. I think we're all going to the park, but sure, sorry, it's not.
Oh no, I'm not on sure.
Well, I mean, maybe they will take a bit of certain people. But they're common fire pictures. Are we not like anything?
Why are you saying who's wrong?
You're going to the park with them? Oh, yeah.
No, he just invited me.
Yeah, I mean,
It was just a statement that shows up. Yeah.
wait,
No,
I think,
no, I
I-
know people.
yeah, come on, sure. Come on, sure, sorry.
Okay, but I just.
I'm having my routine open, but I'm not kidding. Do not go to work. You think so? Yeah, but
Well, I mean, maybe we can take the plan and get back out. They want to go to workstation. Yeah. My notes.
I mean, he's no, it's okay. This is our deal. He's such a good guy.
Yeah, but that guy make him believe they're good.
Honestly, though, they are. He could be starting like percent of all. More than
Maybe
often say.
slowly increasing the utilities.
Slowly increasing the heat. In cahoots with National Grid, Con Ed, or whichever one. Yeah.
Oh, or you might be here tomorrow. Yeah. Oh, okay, yeah. Sorry.
Nobody knows.